The microcompression of ultrasound samples project is designed for use by the Texas A&M Ultrasound Research Lab. Precisely measured compression of samples is critical for using ultrasound to study pleural elastography, among other applications. This project provides even and accurate compression through either constant displacement or constant force. The user input from the GUI is sent to the Raspberry Pi, which uses this information to control the stepper motor. The stepper motor physically moves the compressor plate system, which is monitored by a sensor feedback loop for maximum precision.
The microcompression of ultrasound samples project is designed for use by the Texas A&M Ultrasound Research Lab. Precisely measured compression of samples is critical for using ultrasound to study pleural elastography, among other applications. This project provides even and accurate compression through either constant displacement or constant force. The user input from the GUI is sent to the Raspberry Pi, which uses this information to control the stepper motor. The stepper motor physically moves the compressor plate system, which is monitored by a sensor feedback loop for maximum accuracy.
This is the physical compressor subsystem. It is made up of 3 plates, top, middle, and bottom. The top and bottom plates are for structural support only and anchor in the 2 carbon steel shafts. Additionally, the top plate can be easily removed for maintenance purposes. The middle plate moves smoothly between the top and bottom plates by means of 2 linear bearings. Smooth movement is vital for even compression of the ultrasound samples. Lastly, there is an analog distance sensor. Different distances between the sensor and the middle plate will output certain voltage differences, which can then be fed back into the Raspberry Pi.
The motor used for this project is a bipolar stepper motor. The rotational motion of the motor is converted to linear motion through the use of a lead screw. One step of the motor is equivalent to 40 microns of linear movement. The motor is controlled by energizing its 2 coils. This requires bidirectional current flow, which is implemented through an H-bridge in our L298 motor driver, complete with heat-seeking capabilities. The motor driver is powered through an external power supply of 5 volts, and the motor is controlled by an external power supply, which we have found to be 3.6 volts through our testing. The logic for controlling the motor comes from the Raspberry Pi, which is connected here through the enable pins. The Raspberry Pi controls the order of current implementation, which goes through the H-bridge back into the motor to control the movement.
Hi, I'm going to go through the software portion of our project. So if you look, starting over here, this is the Raspberry Pi. This is the main controller of the entire system, acts as the brain. Right here, these are the GPIO pins, and you can see we have several hooked up from here into the breadboard, which then connect to the motor driver and then to the motor. These pins act as the interface between the motor and the software. Now I'll demonstrate the software very quickly. I run it like this. This is the main software interface. It gives you 4 options for use. Loop, which basically runs it in a continual loop, which is mainly used to get measurements and readings, mostly for troubleshooting purposes. Displacement allows for an actual distance. Steps is specify the number of steps the motor should take, and time, you specify how much time you want the motor to run. So for the sake of this demo, we'll do displacement. It asks if you want full step or half step mode. We'll use full step. Asks how much the motor should move. We'll do 8 millimeters. And then it asks if it should move up or down, and we'll say down. And then asks for a speed. We'll say 5, which is the fastest. And so as soon as I press enter on the keyboard, you should see this washer move 8 millimeters down, which it just did.
Now I'm going to walk you through the basic graphical user interface, or GUI, that will be used with our system. This GUI is written in Visual Studio's 2013 and utilizes the program language of C. This language was chosen to allow for greater ease of use for potential communication between the GUI and the ultrasound machine in the future. What is currently up is the main menu of the interface. As you can see, there is a picture on the left-hand side of the framework itself. This will later become a full working animation that shows the middle plate in motion instead of just a picture. Now on the right side, the user will be able to decide on which set of values they would like to adjust on the system by checking one of the two checkboxes and clicking on the Generate button. Because there is no feedback loop integrated with the analog distance sensor in place at the moment, once you enter in the number of micron, for this example we'll use 45, and you click the desired checkbox and then create Generate, down below the current field will become 45 microns. By selecting the Generate ultrasound image and clicking the button Generate, another window will pop up. This window will later be filled with an ultrasound image once the communication between the GUI and the ultrasound machine is finalized. Then by clicking the Return button, you are able to go back to the main menu. To allow for error corrections, there is a button called Readings in the lower right hand corner. This will bring up a window that has reading values of the analog distance sensor and different motor readings, such as torque, voltage, and current. This window allows for error corrections without having to dive directly into the code. Once you have finished correcting any errors, you're able to click on the Return button and return back to the main menu. In conclusion, we have achieved a lot this semester in terms of individual subsystems. However, we still have a lot of work to do to complete this project for Dr. Getty and her colleagues. The next step is to fully integrate our subsystems together while focusing on applying force to the sample via our motor and plate. We will begin to integrate the motor into the physical subsystem while also connecting the background software with the GUI interface. We will then integrate the sensors with the Raspberry Pi to create a feedback loop while also continuing to design and add features to the GUI with specifications from Dr. Getty. We will also incorporate an external power supply to help power the system, while lastly designing and constructing a case to house the electronic elements in an efficient yet pleasing manner. We would like to thank you for taking your time to watch our video, and we look forward to presenting our subsystems on Demo Day.